our today's lesson is mass spectroscopy. And I'm super excited for today's lecture because I have discovered this whiteboard and I'll finally be using it. And now I've also put up my notes, so it's going to be way easier teaching you all and it will be a lot more efficient. So let's start off. You'll see in some places mass spectroscopy being written as mass spectrometry. So don't get confused or don't get scared, it's just one and the same thing. Mass spectrometry is a technique which is used to determine the mass number and abundance of isotopes. A mass spectrometer allows you to measure the characteristics of molecules by converting them to ions, which can be manipulated by electric and magnetic fields. I've used a lot of technical words here. I'll break down those for you in a while. These are the steps that are required for doing the detection in mass spectrometer. Step 1 is vaporization. Um, Before that, let me just familiarize you with the conditions. The two conditions that need to be met are that your sample should be in vacuum and your sample should be in gaseous state. So for converting the sample to a gaseous state, you need to vaporize it. So that's why it's the first step. Second step is ionization. Third is acceleration. Fourth is deflection. Fifth is detection. You can make mnemonic up to your needs yourself, but yeah, these are the steps and it's pretty easy. You can just learn it like VIADD. So very important. um Acceleration, I don't know, you can make your own mnemonic. Anyways, I've not thought of it and I can't at the spot, but yeah, it's easy. Vaporization, ionization, acceleration, deflection, and then detection. I'll show you a diagram for it. And this is exactly what a mass spectrometer looks like. So you put your vaporized sample here, then it gets ionized, then it gets accelerated, and then it gets deflected, and then it gets detected. So what is there that causes ionization? Basically, you bombard electrons in it, and once the bombardment happens and electrons collide with the sample, your sample gets ionized and it turns to a positive ion. So, positive ion is exactly what you need. And in acceleration, you have electric plates which are negative, and since your sample is now positive, when those ions are moving through those electric plates, they're going to gain kinetic energy and they're going to move at a faster speed. And the fourth step is deflection by the magnetic field. And then finally, at the last stage here, they're going to hit this um, plate and they'll be detected. Fine. Now, moving on, here is the mass spectrum that you'll get finally. So this is for an element, magnesium, and you can see on x-axis we have m by z ratio, which is mass to charge ratio, and on your y-axis you have relative abundance, which is in percentage. And mass to charge ratio, since it's a ratio, it won't have any units. So you can see that Mg24 is 78.9% abundant, Mg25 is 10% abundant, and Mg26 is 11% abundant. So the most abundant is 24, the isotope of magnesium, which has mass number as a mass to charge ratio of 24. So yeah, so you can easily make out from this mass spectrum that magnesium has three isotopes, right? Because there are three peaks, and you can find out their mass to charge ratio and their relative abundances, respectively. Now, mass spectrometry can also be used to determine the relative molecular mass of diatomic and polyatomic molecules. Now, here I have drawn a mass spectrum for a polyatomic molecule, which is ethyl benzoate. On x-axis, in this case, I have mass to charge ratio. On y-axis, I have relative intensity. And let me just see how I can. Okay, yeah, this thing is disturbing me so much. I'm still trying to get familiarized with this board. So, yeah, okay, here's the pen. Finally, now I can breathe. Otherwise, this thing kept me so much at unease. Okay, here. Yeah, finally I can use it. All right, so yeah. So this is the mass spectrum and for ethyl benzoate. Now the final thing I got was this. Now let's make deductions from here. this longest peak is called the base peak. So what does base peak tell you? It tells you that something or is in most abundance. So base peak, the most abundant molecule. Then the final peak here, which is furthest, or you can say towards the right, it will give you the relative molecular mass or relative formula mass, you can say, of the compound. And it's called molecular ion peak, M capital P. So this is basically molecular ion peak. And right next to it, you'll see a very tiny peak, that's M plus 1 peak. People usually tend to ignore it, but it's just there because ethyl benzoate has carbons, right? So carbon 12 we know, and then there's carbon 13 isotope. Carbon 13 isotope isn't very common, but yeah, still it's there. So this smaller peak is formed because of carbon 13 isotopes. I hope it makes sense. And yeah, now mass spectrometry and organic compounds. What's the relation between the two? Let's talk about that. Now, you will be having organic compounds, and for example, let's just take example of propane. Yeah. So once you put this sample, you vaporize it, you put it into your mass spectrometer. So what happens is fragmentation. As in, this will break from here, then at one point this is gonna break from here. So you're gonna get various fragments, and sometimes there will be a cleavage and you'll get just this. So you're going to have various fragments, and those fragments will be detected. So here also that was the case, various fragments were detected, that's why you have so many peaks. So same thing is here, we're talking about organic compounds, you have fragmentation in there, and mass spectrum of an organic compound appears a lot more complex compared to the mass spectrometer, mass spectrum of elements. It's so simple. For elements, it's so simple because you just have the isotopes, but here you have to deal with the fragments. That's why it's gonna be very complex, but everything is just the same molecular ion peak you'll have, which will be which will be furthest to the right, and it will indicate relative molecular mass. Then you have M plus 1 peak, it's because of carbon 13 isotope, and then the base peak is basically the tallest peak, and it will represent the most stable fragment, or you can say the ion which has the highest abundance. So yeah, now I have a few questions that I want to share with all of you. This one, let's start off with this one, and it is that vaporization. Okay, just give me a second. I'm trying to. Okay, never mind. So, this is question number one, which is about mass spectrometry. They're saying after vaporization, the sample passes through three stages before reaching the detector. The first stage is ionization, which occurs at R. Describe fully the ionization process for the element nickel, writing an equation to illustrate it. State symbols are not required. So nickel was our sample. As I said, whenever ionization happens, electrons are bombarded and they collide with the sample. So that's exactly what's happening here. Nickel plus electron, so you get nickel plus 1 plus 2 electrons are removed. So one nickel atom gives away one electron and becomes a cation. Wait, sorry. I think there's an error here. It should be plus 1 electron. My apologies. One electron is removed and it becomes nickel positive 1. So we need a cation. Make sure you don't form an anion. It's a cation. This is ionization. Ionization is a process where a high energy electron is shot into the gaseous atom to knock off an electron or two to make it a positive ion. Now, describe the processes which are occurring at S and at T. So at S, you have acceleration. At T, you have deflection. Ions accelerate, gain speed. Heavier ions move slower and lighter ions move faster and further. Common sense. Ions are accelerated by an electric field. Deflection, magnetic field deflects the beam of ions into an arc. Deflection depends on the ratio of its mass to charge. Then explain why the sample needs to be ionized so that the charged ions can be attracted to the electric plates and magnetic fields. If they were in charge, they were neutral, nothing would have been done, right? So you need them to be charged. And then again, there's a quick question here, which is again about mass spectrometry. Identify P and state its purpose. So P is electric field. It increases the speed of the ions so that they can all move at the same speed. So there's uniformity. Identify Q. Q is an electromagnet. This is going to cause deflection. So there's two ways in which ions following path R could differ from the ions that reach the detector. So why did these just come here? So how are they different from the ones that reach the detector? So they are lighter and they have higher charge. So mass upon charge, we're talking about the mass by charge ratio. So they're lighter and their charge is higher. So that's how they could be. That's how they could not just reach the detector, but they were just left here. Now moving on, we have this is a mass spectrum of butane. I'll just very quickly explain this to you without making the video longer any further. So C, carbon, 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 H, H, H. So this is the butane molecule. Let's see how these peaks are formed. First is formed at 15. Where was the fragmentation? Fragmentation was here. So see, carbon 12, right? 12 plus 1 plus 1 plus 1. So it's 15. So this is due to that. Then you have your other peak, which is here. 12 plus 12, 24, 25, 26, 27, 28, 29. So this is the peak at 29. Then you have this. So 12, 12, 12, 36, 37, 38, 39, 40, 41, 42, 43. So that's the peak at 43. Then the final peak basically gives you the molecular relative molecular mass. So you can simply, as soon as you get this, just look at the final peak and you can tell the molecular mass. And these are some of the fragments that can possibly formed in your organic compounds. So instead of calculating again and again, I mean they'll be repetitive anyway, so it will be very easy for you to memorize, but you don't have to exactly memorize because this is just the mass. It's actually mass by charge ratio, but see, charges are all positive one. So it's basically just the mass. So yeah, these are possible fragments that can show up, and just have a look. And thank you for today's lecture. I hope you all found it informative.